Next panel has to do with geothermal. It's great to see some of our panelists back from last year, but the focus this year will be more on beyond electricity generation. So the panel has got heat, the Earth as a versatile energy source.
Okay. All right. Is this good? Okay. So everyone start thinking now of your questions. We're going to want some good audience questions at the end of this, and we're saving a fair amount of time. So I'm Ken Wisian, Associate Director of the Bureau of Economic Geology, and I'll be moderating this panel today. But first, since knowledge penetration about geothermal in general is not that great compared to like wind and solar, I'm going to do a little bit of a 101 just to establish a baseline of knowledge for this. So as stated, I'm with the Bureau of Economic Geology. I'm a geothermal researcher. That's been my field since I did my PhD in the 90s. So in the 30 plus years I've been in this field, the past few years are by an order of magnitude the most exciting time I've seen in geothermal. There's a lot of new technology coming on. The possibilities are really opening up and new projects are launching, including a half dozen plus here in Texas.
These people.
Yes. So the Bureau of Economic Geology, for those who might not be familiar, we're part of the University of Texas. We're an applied research organization. We're the oldest research arm of the university. We're also the Geologic Survey of Texas. So we're a quasi-agency function. That's about 20% of our work. Most of it is soft money research in very applied energy, economics, and environment areas. So geothermal systems. We're talking about taking advantage of the heat that's beneath us. And they break down in a lot of different ways, but for today, what I want you to remember are just a few simple versions of this. There is conventional geothermal, which is used around the world right now to generate electricity. The US, by the way, is the largest producer of geothermal electricity in the world at about 3.5 gigawatts, but our grid is so large it's less than 0.5%. Other countries generate 50% of their electricity from geothermal. Geothermal, and that conventional geothermal taps natural hot water or steam systems in the ground as the energy source. What's emerged in the last few years and where all the excitement is geothermal anywhere or unconventional geothermal. And taking advantage of multiple lines of improving technology, that taps into the heat stored in the rocks itself, and you extract it through your own means. To bring the heat up the surface. Those are largely, most of the energy or most of the excitement is focused around electricity generation. But what we're going to talk about today is an even lower knowledge penetration aspect, which is the direct use of geothermal and also as an energy storage item. So direct use involves using a wide range of temperatures, but typically lower than what you would use to generate electricity. And you use that in a variety of ways. Many agricultural processes use heat, whether it's drying food or such, pasteurization, distilling liquor. But almost every industrial process uses heat in some way. And that heat right now is largely generated by burning a fossil fuel or using electricity to generate heat, which is in turn generated probably by fossil fuel, very inefficient. But you can use heat in a variety of ways in those processes and really save a lot of electricity and therefore potentially relatively high carbon fuels. There's also another way you can use the earth, and that's more as a battery for energy storage. And we'll get into that in a little bit more in a bit. But it has real promise to be a highly efficient and very scalable and a very friendly method of storing energy, especially when you compare it to, say, large lithium battery banks. And another key aspect is, at least for the energy production other than energy storage, which by definition is kind of a two-way battery thing, geothermal is a base load. It's a 24/7 operation, so you don't have to worry about when the wind is blowing or not, or the sun shining or not. And in fact, in the energy storage realm, there's real good potential for geothermal to be able to level out wind and solar. Store that excess energy that you may sell for zero right now at some parts of the day and bring it back later. So why do we even concern ourselves with this resource? Because there's an awful lot of it. 47 terawatts of energy flow out of the earth into space on a continual basis. That's several times our world energy needs. But the bigger prize is the heat that's stored in the rocks. It's a very good thermal battery. And the upper 10 kilometers of the Earth's crust contains several thousand times our world energy needs in extractable heat energy. It's there. It's just waiting for us to tap it. And whether it's for producing electricity or direct use like we'll be talking about today, it's right there. And it's under everywhere. Texas has really good potential in this realm. East of the Rockies, it's about as hot as it gets. Don't worry about the scale on here, but look at that as a relative intensity or a priority of development map. And you can see that there are areas, I would say the orange and somewhat the yellow areas, are viable today for some uses of geothermal power. This happens to be a map I put together about 3.5 years ago when we were starting to advocate for the Department of Defense to get into geothermal. They jumped in big last year, and I'm very happy to say that now 3 of the military bases here have geothermal projects developing, along with others around the country. So they're a particularly good early adopter, as is any critical infrastructure. So finally, to break down some of the uses of direct use heat. You can see a variety here that may be a little difficult to read, but it ranges across the board. There's obvious use of heating your homes or whatever. Some countries like Iceland even defrost their roads with geothermal heat. But a lot of people forget, and it's a really big deal here in Texas, you can use heat to generate cooling, to do your air conditioning. That'd be a great use. I mentioned some other things. Greenhouses, a lot of northern countries use that, but there's viable applications for that here. Beeswax melting. Malcolm talked about this yesterday at the Capitol, or a couple of days ago. Who would have thought that's a significant use of heat? But there's all kinds of things in here. Industrial uses too. One of the things I don't see on here is the massive use of heat in the oil and gas industry and refining and cracking. So there's a lot of uses there. So plenty of uses. And actually, when you get down to it, generating electricity with geothermal heat gets most of the attention. But when you're doing that, you're actually typically maybe 15% efficient overall in converting heat into electricity. When you're using it directly, your efficiency is like 85% or better. So if you really want to immediately lower carbon, offset dirty electricity production with direct use heat actually saves you more carbon than generating electricity directly from geothermal heat. So an interesting fact to keep in mind. So with that, I'm going to get off, and I want to turn it to Cindy Taff from Sage Geosystems to talk about energy storage.
Thank you, Ken. Good afternoon, everybody. I'm Cindy Taff with Sage Geosystems out of Houston. So when we formed Sage about 3 years ago, we were focused on geothermal, but we got out to the field very quickly because we wanted to prove our technologies, and we discovered in the field testing that we actually had a perfect energy storage solution. So I'll be talking mainly about energy storage today. So the first thing that you should know is pumped hydro storage, even though it doesn't get a lot of media play, actually represents about 90% of the storage around the world. And that's because it's so simple, and it actually uses equipment such as a Pelton turbine that is really simple, low maintenance. And Pelton turbines have been around since the late 1800s. So what we're doing is very similar to pumped storage hydropower, except we're going deep in the earth. So we call it upside down pumped hydro. So how do we do it? We drill a well. We're targeting a depth between 7,000 and 12,000 feet. We're looking actually for a formation characteristic that is the opposite of oil and gas, and it's the opposite of most geothermal systems. We want low permeability to no permeability rock, and we don't want any kind of natural fractures that would give us a secondary permeability. So drill the well, we create a fracture in the rock, and then what we do is we use the electricity when the demand is low to power an electric pump water into the fracture. It tends to open the fracture up like a balloon, and then you have a pressurized system which you can store that pressurized water until the energy demand peaks, at which time you can open up the surface wellhead valves, and that fracture is wanting to naturally close. And when it does, it will jettison the water to surface. You put it through a Pelton turbine, so we also use a Pelton turbine. You spin the turbine, which spins the generator, and you generate electricity. So we did a commercial pilot last year, it was about 1 year ago, in Starr County. We have a test well there. And we were able to demonstrate a few things. One is we can do long duration storage. So if you think about 4 hour to 24 hours, we can also do load following where we let all that water out of the fracture pretty quickly. We demonstrated a round trip efficiency between 70 and 75%, 3 megawatts per well, assuming 9 5/8 inch casing. We can get more with bigger casing, but for this well it was 9 5/8. And then we were also measuring our fluid losses due to evaporation and also due to leak off, and they were less than 2% at the beginning. And as we cycle, we actually build a pressure wall around the fracture, so that decreased to about 1% at the end of the 5 weeks. So again, these are pictures from our commercial pilot. What we did is we did about 50 or 60 pump-in flowbacks. And what we were doing is measuring flow rate and pressure. And from that, we were calculating what the capacity was. And the picture didn't show up, but we had a Pelton turbine out there where we were actually generating electricity and running some of the equipment on location. So this is 2 of the 50 or 60 cycles that we had performed during that March commercial pilot. The one on the left is long duration. So if you can imagine pairing this, so we were storing for 7 hours and then producing for 17. So if you pair this with solar, you can actually turn solar into 24/7. The one on the left represents, if you've got a hot Texas day and you guys know the electricity peaks between 4 and 7 p.m., again, we can release all of the water in a shorter period of time to meet peak demand. So that's what we were trying to demonstrate with these 2 particular cycles. Okay, so where can we do energy storage? So this is a map. The yellow is where we can actually install energy storage. Because we're looking for low permeability formations, but we don't need heat, it's more geographically possible to do energy storage as compared to geothermal. Geothermal is what's in the orange. And because you need the heat at a depth where you can reach it drilling with oil and gas equipment, then it's more geographically limited. The only other thing on this map is the white lines represent major faults. We want to stay away from major faults because that would take our fluid away out of our system. So one of the things that we're doing is we're moving towards our first commercial facility at the end of the year. In December, that means we'll be pumping water and generating electrons. And one of the critical path items is that we have to build a high-pressure Pelton turbine because there's not a mountain high enough where you would need a 5,000 PSI turbine. But we're going deeper than you can go high, so we're having to build this turbine. So we're working with a company in Washington State, and it is actually in progress. This is an artist rendering of a 10-well, 30-megawatt system. So again, we get 3 megawatts per well. So you're looking at 5 acres for the well site. And then we'll need water storage, and depending on the duration that you're looking at, we'll need another 5 to 10 acres. So a total of 10 to 15 acres. So relatively small footprint for an energy storage facility. And on cost, one thing I want to say is we're not trying to compete with lithium-ion batteries for 2 or 3 hour durations. They're going to be a lot more cost-effective than we are. But when you have to start stacking lithium-ion batteries, so 4 hours or more, that's when we can beat the lithium-ion battery cost. So we're considered more long duration, so again, 4 to 24 hours. And then just real quickly, because I know I don't have much time, I do want to say that our technology for energy storage segues into geothermal. So we use the same downward-oriented fracking technology. We use that same technology where we operate the fracture like a balloon, which actually, in my opinion, you're working more with Mother Nature than against Mother Nature, because as you want that fluid to come back, you're just allowing that fracture to close, and again, it jettisons it back. And we're moving the fluid from one well to another in the surface rather than in the subsurface, and that will reduce a lot of the issues that EGS or the challenges that EGS has. So this is my last slide. This just is an overview of how we differ from EGS. So EGS, as you guys know, it's a 2-well system. You're pumping water from one well to another through a fracture. And some of the challenges with that is you have to connect the wells with the fracture. There's a lot of friction when you're pushing the water through that fracture. And so by using the ballooning method, we avoid that friction. And then the last thing I'll mention is that in our systems, we actually don't vent the pressure. The pressure energy will add 25 to 65% more net output. And so we actually keep that pressure energy in the system rather than venting it. So that's it for me, and I'm going to hand it to Malcolm.
So if it's all right, I'm not good chained behind the podium, so turn my mic on if you would. Yeah, I'm Malcolm Ross. I call myself a geothermal evangelist. That means I do anything I can to support the geothermal industry. I teach here at UT with Dr. Wisian. I teach at Rice University. I lobby at the Senate and federal level, state level and federal level. I help with startups. I do my own consulting. I do lots and lots of stuff in the geothermal space. What I'm here to talk about more is direct use things. And what I would describe the business model that Cindy was talking about is the buy low, sell high model, right? You buy cheap electricity and then you sell it when it's high. So let's talk a little bit about, first, let's talk about electricity and geothermal. And I'll start with what I call cold hard facts. Maybe I should call them hot hard facts. And I'm going to end with magic, okay? So hot hard facts. What is the price of energy in Austin? What do you pay your bill? Anyone know on average? 12 is the average, but yeah, you're buying from a little premium. But yes, 12 cents a kilowatt hour is the average here. What you'll find out if you go to the International Energy Agency is, the U.S. Energy Information Agency, you will find out that less than half of that actually goes to the generator. Most of half of that is fees, taxes, add-ons, et cetera, et cetera. So Austin Energy is actually receiving something like 6 cents out of your 12 cents that you're paying for that kilowatt. Now, they're not paying 6 cents to generate that, otherwise they wouldn't be making a profit. So they're probably generating at 2 or 3 cents a kilowatt hour, something like that, and the rest they're making profit. Now, what that means is if you're going to try to come in with something competitive like geothermal electricity, you've got to produce for less than or equal to 3 cents a kilowatt hour. And there's not much margin there. 3 cents, you're just not going to make a lot of money without making an awful lot of energy. And there's just not a lot of energy density in hot water, okay? And by the way, I will comment that the 3 cents generating cost that they have is not a true full system cost, right? That's just what they're getting away with. If you add in the cost of carbon, pollution, environmental, all these other things, then the number is much higher. But that's not the number they're working with, so let's stay at 3 cents. So selling electricity is a very difficult game, and doing it with geothermal is going to be even more difficult. Let's look at it in another way also. Let me show you my first slide here. The creating electricity from hot water is also a difficult game, and Ken mentioned it. These is the production temperature from 100 to 300 degrees C and the utilization efficiency, so the conversion efficiency from hot water to electricity. And these are 4 different types of plants here. 2 are supercritical and subcritical, organic Rankine cycle, you don't need to know the details. And then 1 is a single flash and 1 is a double flash plant. But what you'll notice here is none of them get above 50% efficiency. And in fact, some of them at the lower temperatures are down at 0.2 or 20% efficiency. And that's just the plant. That's not the full thing. There's efficiency loss as you move the heat from the well to the plant. There's other losses. In fact, if you do the modeling on this, this is about double what you will actually receive for the full system. So organic Rankine cycles are usually below 10%, and the single flash, double flash are usually around 30% at best, at the highest temperatures. So not a very efficient way to use the available heat. And Ken hinted at a more efficient way, which is direct use. And here's my version of that same graph that he had. At the bottom is 40 degrees F or 4 degrees C, all the way up at the top at 700 degrees F, some very high temperatures. What I've circled there in black is what I was just talking about, the electricity generation piece of this. The binary plants at the bottom, the the flash and double flash plants above, they start at, well, they say 100 C, that's probably optimistic. More like 125 C and 250 and above. But there's all these other things, and Ken mentioned all these. My favorite one on here is mushroom culture. But there's lots and lots of different things. You don't need to read those. Your general impression would be, wow, there's a lot of other things you could do with the geothermal heat. But the point that I want to make is that with heat, you can actually, the waste heat of one product is the input heat of another. So you can cascade these things. So you could have a perfectly good geothermal plant, and the hot water coming out of it is not hot enough to make electricity. Wow, but it's great for refrigeration and ice making. And then that waste product of that is, oh, that's really good for buildings. And then the waste product of the building is, oh, well, that's pretty good for greenhouses, and so on. So when you're selling electrons, all you can do is sell electrons. But in this case, you can have a multiple revenue stream model for your product and your customers. And each one of those customers potentially are paying you for the heat that you're producing. You can also optimize this. So in the summertime, you may put more hot water towards one of these things, and in the wintertime, more towards another. You know, so there's a real optimization engineering thing going on there. So that's a big advantage of direct use. And you're using 100% of the heat here, not losing 70% like you do with electricity. So let's talk about magic now. And Ken mentioned it. This is an absorption chiller. I'm not going to go into the details other than to say you've got input up there of hot water / steam in a closed loop. You have an output of chilled water. That's magic to me. Well, how does that happen? I'll just point out that there's multiple closed loops here of fluid moving around through various pressures and going from liquid to gas to not to solid, but I don't want to try to explain the physics of what's going on here, but it is making heat from cold. The only other element to it is the cooling tower, and that's the only open part of this system. The rest of it is completely sealed. And just so you know how you can do this, if you want 40 degrees F water, that's pretty cold water, but that's the building kind of mix. You can do that with a mix of water and lithium bromide, both of which are, of course, neutral agents. And if you want to get below 40, if you want to get even below freezing, wow, that's magic. You use ammonia and water. Now, ammonia can be toxic and so difficult to work with, so we don't use that as much. But that's the magic as far as I'm concerned, and that's, I think, the opportunity. And by the way, these systems, efficiencies run 75 to 85% of the heat gets converted into cold in a single stage, and a more complicated version of these, actually the efficiencies go between 1 and 1.5. So you actually make more cold than the heat that you put in. Again, magic. Okay, so let's talk about here, right? UT has a microgrid where they are providing cooling, heating, electricity for the entire campus. They don't buy electricity from Austin Energy unless they have to. And how do they make cooling? They burn natural gas to make electricity to turn around and cool it, right? And I would argue that an absorption chiller would be a far more efficient way to do that with a zero CO2 footprint. So that's what just a little bit of magic that I want to talk about. And I'm sorry, I hope there's probably physics professors here to tell me I'm crazy, but anyway. Yeah.
All right, so how this works. All right, here we go. Can you hear me? All right, hello everyone. I'm Silviu. For those of you who don't know me, I was the chief scientist for the pressure pumping product line at Baker Hughes, one of the largest oilfield services companies. And then I spent 3 years here at UT in the petroleum engineering department. And just this January, I left UT to, I co-founded with Bedrock Energy company to address geothermal heating and cooling of large buildings. And so what that means. Geothermal heating and cooling of buildings is not a new concept. It started probably in the United States. The first one was in Boise, Idaho, a large project I'm talking about, in early 1980s. Famous projects around the country, Statue of Liberty in New York, many universities, military bases, single-family homes, you name it, it's everywhere, essentially. It's not spread it, and I'm going to talk a little bit about why is that. But if you think about what this means is that Cindy and Malcolm and Ken already addressed how much heat we have in our planet. So what we are doing with direct heat for buildings is actually to move the heat between the building and the subsurface. And so we are not creating heat by, burning natural gas or converting geothermal energy into power and then back into the heat. What actually we are doing is literally moving the heat from the building and the subsurface. And so because of that, we need actually energy just for the, moving the heat. And so this is why geothermal heating and cooling systems, also known as geothermal heat pumps, ground source heat pumps, geo-exchangers, heat exchangers, you name it, they are so widespread. However, if you look at all the large buildings in the United States, or let's say all the buildings in the world, they are responsible for literally 25% of the energy use. And so it's a very large sector, and so we need to address it as such. We started Bedrock actually with the purpose of decarbonizing buildings like this one. So a very large building, somewhere in a dense urban area, where actually the current technologies from oil and gas are not accessible. And so what that means, if we want to retrofit a building like this to geothermal heating and cooling, we'll have to address all the problems of bringing the drilling technologies from oil and gas literally here next to it, and then drilling hundreds of boreholes probably for a building this size, and then connected it to the HVAC system of the building. It's a lot of work. And so the way the industry works today, and I'm happy to elaborate about this later, is that if you want to do a system like this in a building like this, you will need to involve currently probably 4 or 5 companies. That means a very slow process, very expensive, and probably you will have to deal with different parties for maintenance and for making sure that it's working to the specifications that you want it to do. Yes, you will lower your energy bill. Yes, you will decarbonize your building by probably 90%. Depending on what study you are reading. But the technology exists today. And so to scale it up to any building in the United States, and especially large buildings like this one today, we will need actually to develop technologies that are affordable, compact, they are efficient, and they are fast. And so this is how we started Bedrock. When we talk about how we can scale up geothermal heating and cooling to any building in the United States, what we realize is that all other geothermal companies out there are addressing one problem at a time. So they are either project developers, they are either technology developers and such. Bedrock is actually a vertically integrated company. Our counterparts from the oil and gas industry are, companies like Baker Hughes, my former company, Schlumberger, Halliburton, Weatherford, you name it, right? And so what we are doing is literally developing technology in one place, and then we are drilling ourselves, we are installing the systems ourselves. We are one shop for everything. And so this truck shown here it's our drilling truck, the first version that we just developed. We manufacture it and we just deploy it in South Austin, on South Congress, right in the city. We already show that this truck is capable to of drilling 3 times faster than the available technologies on the market today. We also have the intention to drill much deeper than all other geothermal, companies for heating and cooling of buildings. For instance, here in Austin, as I said, there are many projects, especially single-family homes. The current rule of thumb for the industry is that no matter where you are in Austin, you drill 300 feet. So that means that actually you don't drill for temperature or for heat, you drill for depth. And so what we are doing is we build all this, drilling technology, and then we are drilling literally for the temperature that we need, for the building size we need. And so by doing that, we are able to drill between 1,000 and 2,000 feet, no matter where we are, and that is dependent on the location of the building, the size of the building, the weather pattern in that particular location, and so on. This is a step change, but where we are going to get with all that is that once we can prove that not only we can drill, deeper, we can drill faster, but it's about actually how we execute a project as well. So our vision is to come up with all the knowledge from oil and gas, from the tech industry, and from the real estate. And so this is why we built a very diverse team with a lot of different expertise and experience. And we bring everything together, we package it all together. And so the intention here is not to do every building the same way, to drill the same way, and to execute projects the same way. We have to come actually with a way to address the exact needs, heating and cooling needs of each building, and each project is going to be predictable. So how are we going to do that? Coming from oil and gas, we don't produce oil and gas from any location. We have to do exploration. We have to do a lot of simulation to understand exactly, where we can produce oil and gas and how much. So we really characterize our subsurface conditions, and we understand exactly how we produce, for how long to produce, right? The same thing we are bringing into the geothermal heating and cooling industry. So without that predictability, without that consistency of executing projects for geothermal heating and cooling, you pretty much are going to have a payback period, and I'm saying that because we are in the business school here. You can have a payback period anywhere between 5 years currently to all the way to 26 years, University of Illinois at Urbana-Champaign. And so that's actually the big blocker for executing and scaling up geothermal heating and cooling projects. I'll let Ken now take it over. Thank you very much.
Okay, it's time for y'all to talk. We need some good questions for the group up here. What have you got? Anything at all? Sir, let the microphone get to you if you would.
I don't know how good a question it's going to be, but, and I appreciate y'all coming here, really do. The idea of the efficiencies you're bringing up, and I too believe in magic, so particularly where electrons are concerned. But taking a geothermal well, creating electricity, using the waste heat of the water to do all those more efficient processes, is that a cycle that has been considered, and would it push it up to the 60, 70, 50, 60, 70% efficient? And if you had renewables to get the initial pressure going, would it just be a standalone island self-sustaining
Yes,
system?
that's an excellent point. And staging is done both with electricity, staging multiple generation cycles after another, but Malcolm can jump in on the various stagings.
Yeah, it's been done mostly overseas, Europe, and elsewhere. And indeed, that, of course, increases the efficiency because you're not wasting the heat just after the electricity generation, like we do in the US. For example, the Blue Lagoon in Iceland, which is a very popular tourist site, is actually the waste pond of a geothermal plant. I would also point out that it is possible to do things such that, for example, in a data center, where you have geothermal heating and cooling and electricity, and the only thing you're transmitting is the data out the fiber, right? So you can do it all behind the fence for one project. Another would be hydrogen generation. Another would be direct air capture. All of which could be all behind the fence using the geothermal energy, both heat and electricity as a source, with a product that will be a whole lot easier to transmit than electrons.
Good question.
So I kind of asked this to Cindy yesterday after the talk at the Capitol, but orphan or inactive wells, we have a lot of holes already in the ground. Some of those, it seems, might be a little too small for major power, but could some of those be used for direct, or some of the district heating, or for maybe some smaller applications? Does anyone have any thoughts on that?
Let me start off and then turn it over to Cindy. So there's intense interest in what we can do with old oil and gas wells for geothermal, whether it's electricity or direct use. In general, oil and gas wells bottom out at about the temperature that electricity production would start. But there's a lot of heat elsewhere in that column, so that's a distinct possibility. One other thing to consider, though, is where those wells are in relation to where the need is for the heat. The oil and gas field tends to be relatively low population areas, but there's still, what else can you convert it into that's exportable, like crops or whatever. So yeah, it's a definite high interest item from the oil and gas industry.
Yeah, and just to add to it, the challenge with using existing oil and gas wells is they're 5 inches in diameter, and we're needing about 10 inches in diameter because you need the mass flow rate to get these huge volumes of water to bring the heat to the surface. So, in the future, I think we need to keep an eye on it, because if we can get the power plant costs down, and so it might be a source of, low rate electricity in the future, but right now it's just not economic. Good question.
Everyone gets stuck on the production side, but in fact, you could drill a good big well for the production side and use 3 or 4 of these other wells for the reinjection side.
Yep.
However, getting the permitting is going to be a challenge here, because you're going to have to re-permit it from oil and gas to geothermal and environmental studies, and there's lots of other challenges here. But don't get stuck on just the production side. You've got to get the reinjection side too, and I think existing infrastructure may be a good choice there.
Well, thank you all very much. This is super interesting. And I have a question pointed for Cindy and kind of Sage's point of view. As an energy storage product, are you going to market fully merchant, buying low, selling high, like you mentioned? Or are you going to try to contract that out and have certain requirements, or let someone toll that like a battery might be? And I'd love to hear just more generally about the economics of it.
So all of the above. Our investors and ourselves as well, we want to be able to scale very quickly. So, we're partnering with a lot of companies in different states and different countries even. And so, to your point, one application is to buy off the grid and then arbitrage and sell when the electricity price goes higher. Another is to pair with solar. In fact, over the weekend, we were working on what would be the blended levelized cost of energy for solar plus our storage, and we found it to be 5 cents kilowatt hour, which is pretty competitive. So we were, after doing, our president Levering did this modeling, so after doing the modeling, we were quite pleased with that. We've been talking to wind producers that produce all of their, not all of their, but a lot of their wind at night when, the demand is low, and they would love to be able to move that to the time of day where the demand is high. So lots of uses for it, especially in the near term as wind and solar keep getting bigger, especially in Texas and in California. Thank you.
Hi, Cindy. Thanks for coming back and telling us what you were showing us last year. I may have missed it, but coming from the Panhandle, what are the temperatures that you need, i.e. if you've got, say, granite wash at a higher, like Anton Irish versus, deeper, is it a temperature pressure gradient that you have to have, or are you just going on temperatures, and how much water are you using?
If you're referring to energy storage? Okay, no temperature is needed. In fact, we want the water temperature to be less than 100 C when it's going through the Pelton turbine because it can't handle two-phase flow. So we'll target, again, depths of 7,000 to 12,000 feet, and we just don't want to go too deep. The deeper you go, the more the energy density is, but if you go too deep, then the temperature might be too high. So cost of storage is, I think was your other question, is we're looking at a levelized cost of storage of 3 to 4 cents a kilowatt. And then if you have IRA benefits, it can be even lower.
Tax credits aside, just in real numbers, how much water do you really need if in order to scale up something like, say to run an industry that's a mid-sized to small industry? How much, if you say you're only losing 1%, but how much water do you need for your initial feed, and then how much do you need to add?
Yep, good. Yeah, sorry, I should have answered that question. So initially what we're doing is putting a volume of water in the fracture. It'll depend on the duration that you're wanting to produce the water. So if it's 4 hours, it's a smaller volume. So let's just talk about 4 to 6 hours at 3 megawatts. Then the initial volume is about 100,000 barrels. And then we'll be cycling about 20,000 barrels of that. And then, so once you get the fluid in there, we are going to be reusing it, but that's why I'd mentioned the water losses. We would have to have makeup water, but it looks like the makeup water is pretty immaterial at 200 or 300 barrels per cycle. Yeah. Very good questions. Thank you.
So just to add to that, in all these approaches, whether it's electricity generation or energy storage of using the geothermal anywhere, your system is designed to be as close to a closed loop, infinite recycling as possible. So the water use is generally going to be fairly low, but it's a critical question, especially in the arid areas or areas that are already overdrawing their water resources.
Last question.
Malcolm, I love the cascading idea and that whole effect, but how do you make that work? It seems like everything would have to be right in the same location for the cascading effect to work. So how could you make that work over distance?
Yeah, that's true, but I think that's the attraction of geothermal anywhere, right? If you were trying to do this with an existing geothermal plant, you'd be out in the middle of nowhere, California, and what good is a greenhouse there if you've got to drive your lettuce into town, that kind of thing. But if you're doing geothermal anywhere, you can be doing it next to your customer. The idea is, in my mind, is like a business park, where you have at one end of the park is your geothermal plant, and maybe you're making electricity, and then immediately adjacent to it is all the other users, all behind the fence and sharing all the resources needed to make that happen.
Okay, great. Thank you. All right, with that, thank you so much.
Thank you all very much.
Thank you. Thank you.